All right, so welcome to the next part of the course. What we're going to start talking about here, and this will continue on for the rest of this week, most likely, are topics related to an overview of Android. Android is a very large system, as you'll see here in a second. It's probably tens of millions of lines of code long if you take into account all the different layers and different parts and components and so on. And we're going to focus on the layers part first, and then we're going to come and talk about the components part, when we might get to that a little bit later today. So the objectives in this set of slides are really to understand what the layers are in the Android software architecture. There's actually a pattern called the layers pattern. We might cover it later. It's a pretty obvious pattern. It really says if you're confronted with a large, complex design space, rather than trying to tackle it all in one fell swoop, instead break it up and address it one layer at a time. Now, there's a lot of reasons for doing that, one of which is to try to tackle complexity through divide and conquer. Rather than trying to build the whole thing, you layer it so each thing becomes more manageable. There's another reason, though, why people do layers. Can anybody else think of another reason why you might want to layer something? Colin? Abstraction, right? So from the abstraction point of view, you do layers to be able to hide implementation details behind a well-defined interface so that you can vary things underneath but have some stable API or interface that you rely on top. So that's really what abstraction is about. Abstraction is a great example of finding places to be very precise at a higher level of detail. Lawrence?
Efficiency, so you're not having to run everything all at once.
So efficiency, it's interesting. Efficiency actually has a couple of meanings in this context. So efficiency might be computer efficiency. The processor might be able to separate things out more effectively. The other reason that you might do things is for human efficiency, so that you don't have to have everybody understand the whole thing and have to worry about trying to be a master at every layer of the stack, which is rather hard to do, although very lucrative. Yeah?
Orthogonality.
Orthogonality, what's a good...
Well, so if you develop one layer completely and you know that it's tested and it works and it's good to go, then you're not tightly coupled with that.
Perfect. So separation of concerns, right. Defining well-defined abstractions that you can reuse without having to reinvent. Yeah, those are great reasons. There's another thing I'm looking for here that's very much along those lines. Did you have a... The other reason is... Oh, yeah, go ahead. Robbie.
I don't know the best way to describe it, but like storage constraints, kind of. So like when you're like linking different libraries, it's kind of easier to have everything in their own little separate pot, so you can pull things out.
Yeah, great observation. So the observation here is if you break things up in a more modular way, then you don't necessarily have to have it all linked together. You can link just the stuff you need. So it's kind of an on-demand argument, just the pieces you want, not all the pieces. Now that's actually, ironically, not so much an argument in favor of layering as it is in terms of modularity and partitioning. And we'll talk a bit more about this, but in general, if you think about layers, you think about, let's see, there we go. So these are layers, like applications, application framework, Linux kernel, and so on. And what Robbie's really talking about has more to do with partitions within a layer. You might have separate modules. You might have, as an example, different kinds of drivers, and you only want to load in the drivers that you're actually using. You're not going to load into memory the drivers you're not using. So within a layer, you might partition it or modularize it so things are more plug and play. But that's still a good observation. That's a lot about building systems out of pieces as opposed to big monolithic balls of spaghetti or balls of mud. The other reason I was hinting at, which you guys got close to, there are different economic business models at different layers, right? So as we'll see in a second, there's many layers in Android, but those different layers have different companies that play at those layers. So as I go through the layer cake diagram, as we talk about the technologies, we'll also talk about the business models. And that's another motivation for layering. Give everybody a chance to find a way to compete and innovate without having to compete and innovate through the entire stack. Now, if you go to this link here, you'll get this diagram plus some good explanations of what all this stuff means. And I'm going to talk about a lot of it here, but if you want a nice overview, that's a good place to go to look for more information. Android is a vast thing, and we're not going to try to cover all of it. We're really going to cover the part that focuses primarily on the topics in this course, which are concurrency and communication. But there's lots and lots more stuff that we could cover. Okay, so what is Android? It's a layered stack that's tailored for the needs of mobile devices. So that should give you an interesting sort of constraint space. And that figures very prominently in some of the design decisions that were made by the architects of Android. And we'll talk later about what some of those things would be. At the lowest layer, above the subatomic particle level, we have the hardware components. And that's not part of the software stack, although it's part of the Android stack. And it's probably actually a place where there's a lot of competition in terms of a vast industry of people who supply these parts. Can anybody think of some specific examples of hardware components that you might experience with a device like this? What are some things in this that are hardware oriented? Processor, right? So processors nowadays, increasingly on the high-end phones at least, are multi-core. My phone has a 4-core. Most phones have dual-core these days. Kind of have to go out of your way to find a single-core processor device these days. So there's general-purpose processors. Then there's also typically DSPs, right? Digital signal processors, things like the radio and the modem and all the other kind of stuff. There's also parts in there that are maybe GPUs, graphic processor units, things for doing other kinds of processing, graphics and displays and stuff like that. What are some other things that you might find hardware-based on a phone? RAM, memory, yeah, of course. So main memory, and then there's typically flash memory, which are still memory. That's good. Sensors, yes. So accelerometer, speedometer, odometer, all these different things you can use to keep track of where you walk or where you are, and lots of stuff, GPS devices and so on. So it's amazing how much is able to be packed into a relatively small form factor. So that's the core part. Needless to say, we're not going to talk a lot about that layer in this course, but everything that we're going to talk about with respect to concurrency and communication ultimately relate to what the hardware is doing. In fact, in the best of all possible worlds, the operating system and the layers of middleware that sit on top of it should try as much as possible not to get in the way, because the more they get in the way, the more overhead they eat up. On top of the hardware is an operating system, kernel. We're going to come back and talk a bit more about that in a few slides, but in a nutshell, this is it's a variant of Linux. It's the Linux kernel with some extensions that have been added to it, and it's written predominantly in C, and there are a bunch of sort of special purpose things that were added specifically for Android for it to work more effectively with mobile devices. And we'll talk more about that stuff shortly, but in a nutshell, it's things like managing power more effectively, because battery life is very precious in these environments, being able to manage things like memory, keeping track of how much memory is in use when memory is used, when excessive memory consumption occurs, maybe killing off some stuff. So there's a bunch of enhancements that were made in there. There's also some enhancements to be able to do faster communication between something called processes, which we'll talk more about later. That's the units of encapsulation and isolation and protection in Linux, in the Linux kernel and the Linux operating system. So ways of talking between those things. That's all done. That's very low level. We are also not going to talk much about the kernel level other than maybe 5 or 6 slides we'll talk about in a few minutes. So this course is really not about the operating system kernel. I think it would be absolutely fascinating to teach a course at Vanderbilt at some point on the Android Linux kernel. And it's all open source for the most part. You could learn a lot of cool things. And maybe we'll get to that at some point. But that's not what we're doing here. Some of the things that are in there are a driver for interprocess communication, power management, and so on. The next set of layers, they're actually kind of glommed together, are dealing with low-level middleware. And we'll talk more about what some of this stuff is. At the lowest level of this is something called a hardware abstraction layer. And we're going to come back and talk more about this as well. At first, it seems a little bit odd that a hardware abstraction layer would even be a layer at all. Because if there's one thing that an operating system kernel is, it's a hardware abstraction layer. The operating system kernel of Linux, for example, is trying to abstract away from the type of processor, the type of memory device, the type of storage, the type of Wi-Fi card or network or whatever it is that you're trying to do that's hardware. So they actually build something called a hardware abstraction layer on top of the operating system. And you might kind of think in the back of your head before we talk about it, just to quiz yourself, why did they do that? What was the point of all that? So there's this thing called the hardware abstraction layer. We're going to talk a little bit about that. That's not where we're going to focus most of our effort. The next part of a layer is called the Android runtime. a lot of what we're going to cover in this course is in this layer. And I should point out that the hardware abstraction layer is largely C and C++ oriented with a Java binding on top of it. The Android runtime, as we'll see, some parts of it are written in Java, large amounts of it are written in Java, some parts are written in C with a Java binding, so there's a bunch of different things. So the Android runtime is where the bulk of the concurrency and communication libraries come from that we care about in the context of this course. So there's a virtual machine and core set of libraries. We'll talk more about them. Then there are also a set of native C and C++ libraries. So these include various things like databases or WebKit, which is a web browser framework. Of course, libc, which is what provides the C standard library interface to the operating system functions and system calls. Various kinds of 2D and 3D graphics, multimedia streaming, blah, blah, blah. We'll talk about that stuff later. A lot of what Android actually does under the hood is implemented in this library layer, or part of a layer, and then it's exposed up to the applications via the core libraries that are provided in Java. So a lot of what Android does is it encapsulates the efficient C and C++ libraries with Java bindings. And we'll talk more about why it does that later. On top of this stuff is a bunch of middleware frameworks. This stuff is middleware too. It's just more sort of virtual machine and native code encapsulation middleware. It's sort of host infrastructure middleware, as the term is often used. What we're talking about up here is more middleware that's dealing with higher layer abstractions. And there's a bunch of services that are provided by the so-called application framework layer, which again is middleware. And it provides a bunch of services. We'll talk about these services later. They deal with things like the user interface, interactions with the users, dealing with making phone calls, telephony services, managing notifications of various kinds of things, alarms, timers, all kinds of stuff. The bulk of this code is written in Java with some Java native interface calls down to lower layer stuff. But this is predominantly accessed through a Java interface. And then the final piece of the puzzle, from our perspective, is the packaged applications. And these are the things that come out of the box as part of Android. And you'll find them, typically if you have the Android source code, in the packages apps folder, packages apps. So there's lots of cool stuff in packages apps. And there are a lot of things in here. We'll talk about them later. So the browser, email client, calendar, contacts, all that good stuff. Now, typically vendors in practice will also ship their own applications along with the ones that come out of the box from the open source world. And sometimes the vendors will modify them in various ways. And then, of course, when you build an application, when you build applications for this course, those applications are going to end up living in that layer too. It's just that you provided them. But aside from that, they look and feel like any other kind of application. That's one of the things that makes Android or any mobile phone environment particularly attractive as a learning tool, because you can build applications very quickly that leverage lots and lots of framework stuff that lives underneath to make it all faster and easier to work with. Okay, so that's basically the architecture in a nutshell. We'll go through each of these layers in more detail. Any questions about the overall?
So what was the need of the HA, the hardware?
The hardware abstraction layer. So we're going to talk more about the hardware abstraction layer in just a couple slides. In a nutshell, the hardware abstraction layer is there to do two things. Thing number one, it's there to be able to provide common interfaces to devices that don't have common interfaces inside the Linux kernel. So there's certain things that are not typically found in a Linux kernel, like a radio, the radio interface for being able to make your phone calls. That's not typically in the Linux kernel. So they didn't have a well-defined interface that they liked in the kernel driver, so they defined a radio hardware abstraction layer component up here that then is used by higher layers in the framework in a more consistent way. So that's one thing. That's the technical reason. We'll talk about this later. The other reason is that if you put stuff in the Linux kernel, what is the characteristic of stuff that goes in the Linux kernel? It has to be open source because it's part of the GNU public license. So anything that you put down in the Linux kernel has to be available to everybody. Well, not everybody wants to give away all their source code. Some people do, but not everybody. So the hardware abstraction layer is also a place to put stuff that you don't want to give the source code away to, but still is important from the point of view of providing access to hardware-oriented sensors and other components. So we'll come back and talk about that a bit more in detail. Good question. Any other questions about this? Okay. So let's kind of dive now into a little bit more detail about Android Linux itself. So here's a more expanded version of the Linux kernel. If you go to this website, you will find lots more about Android, the operating system. And Android, the operating system, is a version of Linux. I think it's a variant of Linux 2.6 kernel that has a lot of things that a standard kernel has, and we'll talk about those things in a second, as well as a bunch of other things that a standard kernel doesn't have. By and large, all of that stuff is open source. So what does an operating system kernel really do? Well, as I said before, an operating system kernel is really a mediator between higher layer services and applications and the underlying hardware. And the purpose is to shield the applications from those details. So it's basically a facade or a mediator or something. It's a series of patterns that it implements. But it basically abstracts away from those low-level details. So there's a bunch of things that you get with an operating system kernel. So one of the things you typically get with an operating system kernel is something that's called virtual memory management. Now, you may or may not have taken CS281, so I'll have to explain this a little bit. Virtual memory is basically a way of being able to give the program, a program or a system, like a kernel, the illusion that it has a very large address space, when in fact it has a smaller physical address space. So there's a mapping between virtual memory and the actual physical memory. And why do we do this? Why do we have virtual memory? What's the motivation for this? Yeah.
So you can make really large projects that won't fit on your physical memory?
So that your projects, your applications, your programs can actually take up more space than you have access to for main memory. Just out of curiosity, what's the driving force? Remember we were talking before about economics. What's the driving force here? Software's going to run faster, but what's let's see. Clearly your programs are actually stored someplace. They're not pulled out of thin air, right? They exist somewhere. They just don't exist in main memory. Where do they exist? Some kind of disk, probably a flash drive or a solid state disk or something. Might be a hard drive. Yeah.
I was just going to say, and so are you talking about what's the drive to do that? Not just make things large, but also because then you have a virtual place that it's going to, that even if the real place changes, it's fine. You're talking about the...
So there's definitely an abstraction dimension to this, but I'm thinking here more about just good old economics. Right. So let's face it, main memory is pretty cheap these days, right? There was a time when main memory actually was sort of more expensive than secondary storage. So disk storage is ridiculously cheap, right? It's you can buy 500 gigabytes worth of storage on Dropbox for $100 a year or something. It's really cheap, right? But it's also relatively slow, all things being equal. So main memory, or registers or cache, or as you move up the memory hierarchy of speed, the cost goes up. So you probably wouldn't want to spend $5,000 for a phone that had hundreds of gigabytes worth of main memory. Maybe you would actually. The other problem, of course, is what happens when the power goes off, right? Poof, the memory loses its charge, and so the information in there disappears. So the point there is there's an economic reason to want to be able to differentiate between things that are more expensive, of which you have less of, which is physical memory, and stuff that is less expensive and you have more of, but is slower. So there's a time-space cost trade-off thing going on here. And this comes back again to the layers, right? By having layers in the architecture that abstract away from these details, people can compete like mad to come up with faster flash, faster RAM, faster cache, faster disk, right? And those enhancements can be folded into your phone or your upgraded phone every couple of years or every couple of months very quickly without changing lots of other stuff. So that's another motivation from layers, right? All the other stuff in the stack doesn't change when you get a faster hard drive or you get a faster flash, you get a faster RAM or whatever. So anyway, virtual memory is just this mechanism which is actually supported by the hardware to be able to make your program have the illusion it's got a big address space when in fact the actual address space is smaller, although quite large these days, and so you're able to have more things running than actually you have room for. Now there's other reasons too about abstracting, and you don't really care where the memory's placed. So you have a lot more flexibility about how the programs are run, and there's all kinds of clever memory management schemes with sharing of pages between applications. And if you're really curious, I'll talk later about how some of the Android implementation stuff works in this regard. But for right now, just imagine that virtual memory is important. Now, the other thing that virtual memory does for you is it provides protection. And we're going to talk in a second about how this is realized in the operating system kernel. But in a nutshell, you can actually control the properties of memory so that you can give certain parts of the system access to certain parts of memory. So, for example, only kernel-related modules, kernel-related code, can access certain parts of memory. And the reason for that is to avoid application code being able to go in and snoop and find out about things that you don't want them to find out about, right? In a typical Android device where there's only one user, these types of issues are important, but maybe not crucial. In a multi-user system, or a system where you're trying to prevent things from being compromised because of bad hackers creeping around and pulling out stuff like passwords or social security numbers or credit card numbers or whatever, you really want to physically protect stuff. And you physically protect it through virtual memory, which makes it next to impossible to get access to things that you don't have privileges or permissions to get access to. That's basically what virtual memory does. Now, that virtual memory then is organized up into different address spaces. So you've got spaces that are sort of things relating to what are called processes. And a process is the unit of protection and resource management in the Linux environment. Now, when you take the operating systems course, you'll learn more about what a process is. But you can basically think of a process as something that will have certain permissions. It'll have certain resources inside of it, like memory. It'll also have access to other resources it has permission to, like access to disks or files or things like that. So the process can actually be in a number of different states. It can be running. It can be in main memory, running, waiting, or blocked. If the system is running low on memory, then you may want to swap it out or remove certain parts of it. So swapping is how you take the whole process out of memory. There's also a concept called paging, which is a little bit finer level of granularity, which requires more hardware support. And of course, you can also have the process over and done with. When you're all finished, it evaporates and goes away and frees up the resources. So a process is the unit of protection and resource allocation. You'll learn more about that as we go further. And then the final piece of the puzzle at this level is the thread. And a thread is basically the unit of execution of instruction sequences. And any given process can actually have multiple threads of execution that can run together. If you have multiple cores, they might actually physically run in parallel. If you only have a single core, then the operating system scheduler takes turns scheduling the thread to run when it's able to run, or when it's its turn to run, or when it has the resources it needs in order to run, and so on and so forth. So if this was a classic operating system course, we would spend a lot of time on virtual memory, paging algorithms, and replacement schemes, and caching, and so on, processes, and threads. And that's what we would focus on. Since this is not a classic operating system course, it's an advanced operating system course, this is about all we're ever going to talk about these topics, at least for the moment. We will come back and revisit threads later when we talk about Java threads, but that's most of what we're going to talk about now. Any questions about those things? So that's classic operating system stuff. Virtual memory, processes, and threads. You typically can have one or more threads per process. Threads within a process can communicate with each other very easily by either sharing global memory within that process or by passing messages back and forth to each other through queues. When you have processes in threads running in separate processes, they typically have to use some kind of inter-process communication, and we'll talk more about that. Another thing that Android has is it's got stacks for communication, network communication being one of the key things it does. Here's a communication stack that you're very familiar with from a usability point of view. This is the classic internet protocol stack, TCP/IP. So we've got TCP/IP, which is the transport control protocol, and it's responsible for doing end-to-end byte stream, reliable, non-duplicated communication between ports, effectively. And there's other kinds of protocols as well. There's something called UDP, the user datagram protocol. And there's various other kinds of things that they have in Linux that provide you with a protocol stack. Again, lots of great stuff. If you take CS 285, you'll learn more about that. And then the final thing that they have in the kernel that we're going to talk about is the device driver framework. So all those sensors we were just talking about, things like the touch screen, the accelerometer, Bluetooth, USB, all that good stuff, that is accessed in the kernel via a framework for device drivers. And it's actually very, very sophisticated, very complicated. Very few people want to program at this level because it's error prone. One stray pointer can cause the whole machine to crash, so it's a very carefully controlled environment. You don't just let anybody write this code. You have to really sort of know what you're doing. A couple things just as a side note. So back in the day, a lot of problems people had with operating systems like Windows that used to get the blue screen of death, that was occurring because people wrote buggy device drivers in the operating system kernel. And it was hard to debug at that level, and the economics of hardware for Windows machines are such that there isn't much incentive for people to improve their software because by the time they do, the hardware is already out of date. So that was a real problem. And the blue screen of death, if some of you may be young enough not to know what that is as much, but up until about 10 years ago, that was a real problem with Windows. About 10 years ago, they developed some really cool tools for doing various kinds of static analysis at Microsoft. And now they developed a toolkit that people who are device driver writers can run on their device drivers, and it finds lots of common traps and pitfalls with device driver programs in Windows. And so you almost never get a blue screen of death anymore. And that's because they used static analysis techniques and tools to be more effective at detecting common sources of bugs. Okay, so those are the things that you'll find in almost any operating system kernel. Virtual memory, processes, threads, network stacks, local interprocess communication, which we'll talk a bit more about in a second, and device drivers. You'll find it everywhere. Android Linux also has some additional capabilities that you're not going to find in just any old operating system because they're Android specific. One of them is something that's called the binder interprocess communication driver, which is a device driver that's loaded into the kernel, and it is optimized to send information very quickly back and forth between processes in Android. And we're going to not talk a whole lot about the binder driver, but we're going to talk a lot about the binder framework and about higher levels of middleware that layer on top of that, things like the Android Interface Definition Language, AIDL, as well as a whole pile of other stuff that uses this, messengers, intents, and so on and so forth. The RPC mechanisms are remote method call mechanisms that use the binder. So that's a big deal. The binder actually came from an earlier project that was developed by some of the engineers before they came to Android. It was called Open Binder, and it was done by a group of people working on the B operating system, BEOS, B-E-O-S. And what's interesting is if you go back and you kind of look at the early work on BEOS and the binder, Open Binder mechanism, the people came to Google with that expertise, and they brought their patterns and they brought their framework approach to Android. And it's very much the same kind of thing. I should also point out, if you do much searching around on the message boards related to Android, you'll find some of the core Android engineers are fairly active on the forum. And one of the lead people is a woman named Diane Hackborn, which I think is such a cool name. You know, it's like, I was born to hack, right? And she's very, very well versed in all things Android operating system kernel. She wrote a lot of the code. Another thing Android has is some support for shared memory. Actually, the binder, one reason why the binder is a high-performance binder is that some of the communication that takes place between the sender and receiver in the binder driver uses shared memory to move the data around to avoid extra copies. So they have Android shared memory that's used for that. There's also shared memory that's used for other kinds of things. Shared memory is a blessing and a curse. It can make things more efficient, but it can be error-prone, and it also can potentially be a security hole, because people can poke around and sometimes get access to things they shouldn't get access to. So this is typically not used by application developers per se, but it is used by the underlying system itself. Android is a mobile device environment. Battery power and maintaining battery lifetime is important. There's a whole set of things in the Android kernel that deal with power management, ways of being able to set the device in different modes based on battery levels, based on usage patterns, based on settings that you have, and so on and so forth, all trying to optimize the lifetime of the batteries. And then the final thing here is something that's called the low memory killer. And this is kind of an odd thing to put into the operating system kernel at some level, but it's there. And basically its job is to shut stuff down when higher layers of the Android stack determine that there's not enough memory to go around. This was really a big deal when Android first came out, because when Android first came out, the amount of, which was 6 years ago or so, the amount of memory that people had in their phones was much more limited than it is today. Nowadays, it's not at all uncommon to have 4 gig, 8 gig main memory, maybe more. It's just incredible how much memory you have on a phone. But when it first came out, it was more like 200 megabytes. And so conserving memory was really important. And a lot of the weird things we'll talk about shortly about how Android components work have to do with the fact that they were built in an environment originally that had to be prepared to shut stuff down at a moment's notice because it was running out of resources. Okay, that's the Android Linux kernel in a nutshell. So that was 10 minutes about the kernel. Any questions about the Android kernel? Again, we're not going to talk a lot about it in the class. It's there, it's cool. If this was a different kind of course, we would spend a lot more time on it. The next topic is the Android hardware abstraction layer. Does anybody know what that is? That's HAL, right? Yeah, so that's the hardware abstraction layer. That should be their icon. And if you've never had a chance, you should devote 2.5 hours of your life to watch the 2001: A Space Odyssey. Not so much because it's really that interesting of a movie. Major parts of it are mind-numbingly boring, but it's a classic piece of culture that everybody should know. And that's the thing. Oh, I do have to show you something interesting though, based on that. So, does everybody know the secret of the acronym HAL? So that was HAL, right? And that was actually IBM minus minus. Right, so that Arthur C. Clarke, who was the author, did that intentionally. So HAL is basically a play on IBM. Here's something you probably didn't know. Anybody know what this is? VMS was a classic operating system developed probably in the 70s and early 80s. Still in use today, not as widespread use, but VMS was an operating system. And the guy who developed it was named David Cutler. David Cutler went to Microsoft, where he invented Windows NT, which is VMS++. So how's that for obscure trivia, right? So he brought with him his knowledge of the patterns, just like Diane Hackborn and the team from OpenBinder and BIOS brought their patterns to Android. He brought his patterns from VMS to Windows. And if you look at the Windows NT operating system, it has a lot of a VMS flavor to it, which is kind of cool. Okay, so there's HAL. The HAL does a couple things. It helps to separate the Android platform logic from the hardware. And it also helps to separate the framework layer from the operating system layer. So what the heck does all that mean? Well, first of all, if you want to know more about what the Android hardware abstraction layer does, there's an article that you can download from my website that goes into it in much more detail. I think it's actually a set of slides. Basically, it's a user space library written in C and C++. So it's in user space, which is kind of weird because usually device driver-like stuff is down in the operating system kernel for a whole lot of reasons. Basically what it does is it defines an interface in C and C++ that Android expects hardware drivers to implement. So all the higher layers, this whole thing about the platform from the hardware, the higher layer parts of Android use those interfaces in order to be able to access the lower level stuff like the camera, GPS, the radio interface layer, and so on. And so that's what you would see. If you were implementing the radio interface layer, you would be programming to the HAL as opposed to the device driver. Some reasons, as we talked about before, for having a user space HAL are technical. As we talked about, things like the radio interface are not supported in a standard way by Linux kernel modules, kernel drivers. Same thing's true for cameras. There are a lot of things you expect to find on a mobile phone you might not expect to find on a laptop or a desktop. So they just weren't in the kernel, so they put them in the user space. Other motivations are non-technical, as I talked about before. kernel device drivers are covered by the GNU public license, which forces you or requires you, mandates you to expose proprietary intellectual property. You can take a look here at the license if you want to learn more about the license. Not everybody's willing to do that. In fact, major people selling Android don't want to give away all their secrets because their competitors will steal it and use it for something else. So most implementations of the HAL components are actually not available in open source form. So there's technical and non-technical reasons for doing that. All right, that's it for the HAL. We're not going to talk about the HAL anymore in the class. Just want you to be passingly familiar with this. Now things finally start to get interesting. So now we're going to talk about what's called the Android runtime, which coexists in a layer along with some other stuff called native and the native C and C++ libraries. The Android runtime basically is used to support concurrent execution of Java applications on mobile devices. So this is really important for our purposes. The bulk of what we're going to cover is covered here. The first part in this thing is actually, oops, let me zap something real quick. The first thing we're going to talk about is its support for virtual machines. So first of all, what's a virtual machine? Well, before we can answer the question, what's a virtual machine, what's not a virtual machine? What's the opposite of a virtual machine? A real machine, or a non-virtual machine, or a physical machine. Okay. So what is a physical machine? Give me an example of a physical machine.
OS X is running directly on my Mac's hardware.
Running directly on the hardware. So what is being run, or let's use the word executed, what is being executed, and who is executing it, or what is executing? So what's being executed? Well, more specifically, OS X assembly, or assembly code translated into machine code. Machine code is being executed, and what is executing it? The processor, right? So that's a physical machine. That's a real machine. So a virtual machine must be doing something along the same lines, except it's doing it virtually, not physically. So if you go here, you will find that there's a discussion about what a virtual machine is in general. And here are some of the things that a virtual machine has. It has something to load stuff into memory. It has something to verify that whatever's being loaded is correct, which is not usually the same thing as you have in a physical machine, which is important. You have some kind of garbage collector, an interpreter that interprets some kind of codes, a compiler to compile stuff, a scheduler, and so on. So that's the kind of thing you typically find in a virtual machine. Now, there's a couple of different kinds of virtual machines. There's what's called a system virtual machine, and things like VMware would be an example of that. And then there's also what's called a process virtual machine. What we're talking about here in Android is a process virtual machine. If you go here, you can find out more about what a process virtual machine is. And what that basically does is it executes stuff, except it's not executing machine code. It's executing so-called byte code. And that byte code is actually generated from Java code via some kind of Java compiler. And then that thing is loaded into the virtual machine where it's actually run. And it basically runs inside a normal application running inside an operating system process. So basically the virtual machine is a layer of software that's running in the context of an operating system process. When the process is created, the virtual machine is created. And when the process goes away, the virtual machine goes away. Now, again, without getting into too much detail here, but it's really cool, Android has some really interesting optimizations to make it fast to load the virtual machine into memory. And the way it works is using something called the zygote. And the zygote is basically a process that when the Android kernel, when the Android system boots up, the Android operating system boots up, it starts a process called the zygote. And the zygote has loaded into it pretty much every single library that Android has, whether it be in C, C++, or Java. So it's got everything in it. And whenever you start a new application, the zygote basically does what's called a vfork. It creates a logical copy of itself, but doesn't make a physical copy. It just does a logical copy, which involves updating some counters in the virtual memory management system. So it's really fast to do. And what happens is that all the stuff that was loaded when the Android system boots is magically copied into the new process. except it's all there. So startup time is basically non-existent. So it just starts right up. And so the whole idea here is to optimize startup time by basically forking the zygote. I'm not going to quiz you on that. It's just an interesting thing to know about. The virtual machine abstracts away the details of the underlying hardware. So you don't have to know or care whether you're running on an x86 instruction set or an ARM instruction set or something else, right? So the virtual machine's job is to abstract away from these kinds of things. The other thing that virtual machine does in general is it provides a managed runtime environment. And that means it can check stuff that would cause problems in a native or real machine environment. Yes, sir?
Are all of the virtual machines that are getting an instance, are they all identical?
Well, good question. So let's take a look at an example. So when you launch an Android application, when you take your phone out and you click on a button, what happens is a process is created through this zygote-like mechanism. And inside that process, so here's the process, this gray box. And inside the process is a bunch of stuff. So you've got things like libc, which is already there. That's the C libraries that are used under the hood by a lot of the native code. You have the virtual machine, which we'll talk about in a second. You've got all those core libraries that we're talking about up here. That part's pretty much the same every time. And then you have the stuff that is specific to your particular application. So if you're launching the browser, you're going to have some browser-specific code. If you launch the contacts application, you'll have some contact-specific code. And we'll see later that these typically come in initially in the form of stuff like activities or other Android components like content providers or services or broadcast receivers and so on. So a bunch of the stuff is common, and that's what the zygote has already got in its core when it starts. And when it does a virtual fork, all it's really doing is just loading in the stuff that differs. So a large part of it is the same, and then the part that you wrote or someone else wrote is the different part. So that's kind of the way things look under the hood. I'll point you to some resources to learn more about this. Now, Android applications are typically run in standard Java. So you're using more or less the kind of Java that you're familiar with if you took CS 101 or you've just had experience to Java, and we'll talk more about that in a second. However, and this is the origins of a major lawsuit between Oracle and Google, they don't actually run in a standard Java virtual machine. So they actually run, at the moment, in what's called Dalvik. And if you go here, you'll learn more about Dalvik. I'll show you some other stuff about Dalvik as well. So Dalvik is basically a virtual machine. It's the Android virtual machine. And it has to do with like the hometown of the guy who developed it. I think his name's Dan Bornstein or something like that. And if you go to these links, you'll find out more about him. Dalvik has bytecodes. They're not the same bytecodes that are the standard bytecodes with Java virtual machines. But the Java code that produced those bytecodes is essentially the same. But the bytecodes are different, and the actual architecture of the virtual machine is different too. So without getting into too much detail, the Java virtual machine uses a stack-oriented set of bytecodes, which push and pop things off of a stack of instructions. Dalvik uses what's called a register machine. So it doesn't use a stack in quite the same way. And if you go and watch this video here, you'll hear the author of Dalvik talk about the choices he made and why he did those choices and why he thinks his approach is better and so on and so forth. So it's worth looking at. It's a pretty cool video. It's probably out of date, but it gives you a good starting point. There's a program called DX that transforms Java classes, not .java stuff, but .class stuff, right? The Java class files that have the bytecode format into the Android DEX formatted for Dalvik executable formatted bytecodes. That's all handled for you automatically by your runtime environment. And in classic Dalvik, there was something called a just-in-time compiler. And what a just-in-time compiler does is it takes a look at the bytecodes that are being interpreted, and it looks for patterns that are occurring frequently, and then it compiles those patterns, and then it executes that code. So it's kind of a hybrid model between a purely interpreted virtual machine versus one that's running things at native speed. Any questions about that? There's so that's classic Dalvik. I would pretty much guarantee that everybody here is using a version of Android that has classic Dalvik. Dalvik is being phased out in favor of something called ART, which stands for Android Runtime, which is confusing, by the way, because Android Runtime is also the name of this layer in the Android stack, and now it's also the name of their virtual machine, which is even more confusing, but ignore that. Just call it ART, and it won't be quite as confusing. So you can go take a look here and learn more about ART. ART uses an ahead-of-time compiler instead of a just-in-time compiler. And what an ahead-of-time compiler does is it tries as much as possible, given the semantics of Java, to turn the Java code into actual executable code instead of turning it into bytecode. And one of the consequences there is that it can run a lot faster because it's native code with callouts to certain sort of library routines under the hood that handle some of the semantics of Java that need to be late binding in their behavior. But it makes it possible to run things much more quickly. The potential downside is that your programs get to be a little slower to load, but a lot of this transformation takes place when you download your app into the phone. So what Google is hoping is that ART will be way faster and people won't notice some of the startup latency, which I don't think they would probably. So ART uses a ahead-of-time compiler, Dalvik uses a just-in-time compiler. If you read this article in Wikipedia, it talks about the difference between ahead-of-time compilers and just-in-time compilers. And it's kind of a classic time-space trade-off.
Was there soon ahead-of-time compiler and like a normal compiler where you just compile it all by machine code?
So when you say normal compiler, you're probably thinking about a compiler for C or C++. That is a way ahead-of-time compiler. So it does all of the stuff when the C or C++ compiler gets done generating the code, then by and large, what's available in the program image that will be loaded in and run is actually the bytes. It's just native bytecode. In a few places, the semantics of C++ will require some runtime management of things. Exception handling would be a good example. There's some runtime stuff that has to take place, and it's complicated, but it's hidden from you. With Java, because of the semantics of Java, you can't fully compile everything way ahead of time. You have to kind of defer certain things because of the semantics of checking of the code and late binding and so on have to be done at runtime. So the code that's generated is not purely binary code that's just ready to be run. There's a mixture of some code that's binary code that's ready to be run and some code that actually has to make calls to library routines to check certain kinds of things. So it's kind of a hybrid, whereas a purely interpreted model would take a look at every bytecode and interpret it in software. So it's kind of this mixture between totally ahead of time, which ends up being binary instruction sets that run on the processor, and purely software interpreted one bytecode at a time in software, somewhere in the middle. And an ahead-of-time compiler is going to do more things ahead of time, hence the name, than a just-in-time compiler, which waits until the bytecode is loaded in to do its optimizations. So it's basically just an evolution of compilation technology applied to Android. Android's virtual machine implements some parts of Java concurrency in the virtual machine itself. In particular, I'll explain what I mean by that in a second. In particular, it's what's going to be mapping things to the underlying cores and the threads, so that's part of what's handled there. And the other thing that's handled in the virtual machine level are support for the built-in synchronization primitives in Java. So what would those include? For anybody who knows?
Like the synchronized keyword?
Synchronized keyword, great example. Synchronized keyword, synchronized block. So those are things that provide so-called mutual exclusion. Yes, Robbie?
Semaphores and condition variables?
No, but you're on the right track.
Runnable interface?
Runnable interface. You mean when you say Java thread start and that stuff? Yes, that stuff is implemented by the virtual machine. We'll actually go through that later in detail. We'll look at the path through the code when you call start. Yes, sir? Monitors, right. So the synchronized keyword is a piece of something called monitors, or what I like to call as monitor objects. Synchronized keyword gives you half of the equation in terms of what's called mutual exclusion, and then the other half of the equation is this support for coordination or cooperation. And monitors give you both mutual exclusion and coordination/cooperation. So you can schedule how things run by signaling, or rather notifying and waiting. What you're talking about is actually handled at a slightly higher level. So semaphores and condition objects and reentrant locks and reentrant read-write locks and countdown latches and cyclic barriers, blah, 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 blah. Those things are handled by user-level libraries, which are actually part of the core libraries we'll talk about in a second. They're not actually handled by the virtual machine. Having said that, almost all those libraries at their core end up using native interfaces to hardware test and set instructions. So they're very efficient. And we'll talk more about that as well. But if you go and look at the virtual machine in Android, which, by the way, I recommend you do, it's interesting to poke around in it, you'll see that they have the implementations of these core mechanisms. So that's the virtual machine layer. You are very, very unlikely to come upon anything in that layer in your work in this class. It would be a miracle if you did that. In fact, it's probably a sign that something's gone wrong if you're at the virtual machine level. But it's kind of cool to know about, and there are people who still do work on virtual machines. It's an active area of research and so on. Much more likely are you, if I want to speak like Yoda, you are much more likely to come in contact with core Java classes, which is something Android also provides. So the Java classes, the Java extension classes, and so on. And these would include all the classic Java stuff: Java lang thread, Java lang, string. There's a gazillion of them. All the things you know and love about Java class libraries. That's part of the core libraries. Android doesn't support every last piece of Java. And you can take a look at this link to find a comparison of the Java and Android API, but it provides an awful lot of it. Then there's also the Android classes. And these are where we're going to focus a lot of our attention, because this is the stuff that actually handles the really cool support that Android provides for certain kinds of things. And part of that are the Android concurrency frameworks. And that's what a lot of the course is going to focus on. And we'll talk more about those in a second. So these are things that basically go above and beyond what you get out of the box with standard Java in order to provide a concurrency infrastructure that is tailored for the needs of mobile devices that run in the constraints of the Android design space. And the two main frameworks we're going to talk about, one of them is called Handlers, Messages, and Runnables, or the Hammer framework. And I need to put my hammer here somewhere. And basically, the Hammer framework allows operations to run in one or more background threads and then give their results, if any, to the so-called user interface thread. To program with the Hammer framework, however, you have to understand handlers, runnables, messages, and threads. So those are things that are something you have to actually be aware of as you program it. Now, it does a lot of really cool stuff, and we'll look at this stuff in great detail later, but you have to be aware of how to program those kinds of things. There's also something in Android called the async task. So there's an async task framework, which sounds very similar at first glance. It allows operations to run on one or more background threads and publish their results to the user interface thread. However, you, the user, don't have to manipulate threads, runnables, messages, handlers, That's all handled for you by the framework. So we're going to cover both those frameworks. You're going to get a chance to program with both those frameworks. They're very interesting. And they also embody some really cool patterns, and we'll look at that in a minute. Some other stuff that Android provides, we're going to spend a lot of time on, are the so-called services. And we'll talk more about services maybe at the end of the class, but certainly next class. A service basically is a way of being able to run some computations, quote, in the background, independently of whether there's any application at the moment that happens to be accessing it. We're going to look at lots and lots and lots of source code in this class related to Android. So if you have a chance, you might want to go and download the source code and pick whatever version you want. I typically stick with, I think it's Ice Cream Sandwich, just because I happen to have it on my machine. There's newer things that have occurred in Android that are also worth taking a look at, but that's a good one as any to start with. The core stuff is more or less the same. Okay, any questions about the Android runtime? Like I said, that's the bulk of the class, is the stuff in there. There are also a set of native C and C++ libraries that are part of the same layer that the virtual machine is on. These things can be accessed using the native development kit, the NDK. Not a common thing to do for the kind of stuff we're doing. If you're writing system services, then you would probably use the NDK, but we're not really focusing on that. There's also a lot of things that are accessing these libraries through the Java native interface. And the Java native interface there's a couple variants of how this works, but I think there's the Android native interface and the Java native interface. Basic idea is it's a way for Java code to make callouts to C and C++ code. And I'd be happy to show you at some point how it works. You put the word native in your Java class, and then you have to provide a .c or .c++ implementation that maps the native method, or maps the Java variant of the method and its signature down to the corresponding native implementation. And that native implementation is written in C or C++, and it gets the Java parameters passed to it in a very stylized way. We're not going to do much, if anything, in the class with that, but be aware that that's how a lot of stuff is implemented under the hood. Here are some of the key libraries that are part of the native C and C++ libraries in Android. So there's the System C library. If you've done any C programming at all, some of you have, some of you haven't, this would be where you'd find the C-level library, standard library functions. So the string functions, file functions, time and date functions, those kinds of things. The thread functions. Yeah, Robbie?
Do they restrict you at all from all the C system stuff? Like any of it?
If you're programming at the question was, are you restricted to accessing the C-level stuff? You're really not restricted, except you have to be programming at the NDK level or the JNI level. But you can access the libc code at that level. So they have standard C library. There's a audio-video streaming library that they have in there for doing media, playing movies, playing songs, and so on, all written in C and C++. Very complicated. There's an open source web environment called WebKit, which ironically was developed by Apple, which is kind of funny because this is Android. But almost everybody in the mobile world uses WebKit as their web browsing toolkit. There's 2D and 3D graphics supported with OpenGL, graphics library, graphics engine. There's something called SQLite. We're actually going to look at SQLite quite a bit later in the course. That's essentially a relational database engine that's meant for relatively small footprint embedded systems like mobile phones, that has pretty much full support for the SQL, relational algebra, and relational query operations. And then there's also support for so-called secure sockets. So you can use those to open secure socket connections to be able to communicate with web servers and web services and e-commerce and that kind of stuff. So those are some of the key libraries. With the exception of SQLite, which we will access through Java, we're not really going to use a lot of this stuff in the class. Just is interesting to be aware of it. Okay, the last layer or layers in this stack are the application framework and the application layer. So the application framework layer is basically responsible for providing services that are essential to the Android platform. And if you go here, you'll find some cool videos that talk about how the Android application framework layer is designed. Here are some examples. It has a window manager, which is obviously handling the way that things are displayed, dialogues and prompts and output is displayed to the window. There's a package manager, which is used when you download apps from the App Store to basically check them and then deploy them into the Android runtime environment. There's a telephony manager, which is used for managing the phone, all kinds of things that have to do with the phone. There's an activity manager. We're going to look a lot at activity manager, probably starting next time, which deals with lifecycle issues, with starting your activities, with starting and stopping them, pausing them, resuming them, and so on, and navigating through the task stack, which we'll talk about later. That's pretty much how you get applications to work together. And there's a task stack. You can go back and forth. When you go hit the back button, you're going up the task stack and so on. There's a location manager that keeps track of where your phone is, and you can use it for things like maps and navigation and other stuff. And then the final piece of the puzzle for the Android distribution are the applications that come packaged with the system. So some of the standard ones that come packaged are the ones here. They're written typically using Java with JNI calls, of course, used to implement the stuff under the hood. Here are some of the examples. Oh, and by the way, whoops, come on. The packaged applications that you get with Android, get this back up here, use the concurrency and communication mechanisms very heavily. So if you download the Android release and you look under packaged apps, or I think you can also look under packages providers, you'll find a lot of the stuff that I'm talking about here. And if you search around, you'll find lots and lots of examples of the concurrency frameworks and services and the Hammer framework and the async task. It's all kinds of cool stuff is in the packaged apps. That's a good place to go if you really want to see industrial strength Android code. Take a look at what's in there. And it's very, very cool. It's very complicated, but also very cool. Okay, any questions about that? So that's kind of a whirlwind tour of Android. Like I said before, we're going to focus primarily on the part having to do with the runtime, the Android runtime, which deals with concurrency, services, content providers, SQL, communication services, that kind of stuff. Those are the main things we're going to focus on in this particular course.